Ogün is going.
Okay, thank you very much, Efe. So, hello, good morning, everyone. So, thank you for being here. It is very early, and we started at 8 a.m. So, earlier than usual. At least we start at 8:40 earliest. But yeah, thanks for being here. And my name is Ogün, and I am a faculty member at Sabancı University in Istanbul. So I have been a group leader for 3 years. I was trained in molecular biology and genetics. Then my undergrad degree was from Turkey. Then I went to United States and got my PhD in computational genomics, basically. And then I had several years of postdoctoral experience. Then I moved back to Turkey. So yeah, I have been interested in comparative genomics, rare diseases, and DNA repair, DNA damage and repair, basically. So I have a computational genomics group. Yeah, this is all about me. Today, we will cover some materials on pairwise sequence comparison, multiple sequence alignment, as well as phylogenetics. So this is not going to be sort of full course. So normally I give these courses in 2 to 3 weeks. However, it's going to be a zipped format today. So I hope it will work out fine. So we have a sort of small group, which is so okay. And it is actually nice because you can ask questions. So one advantage of being sort of participating actually in these lectures is be able to ask questions, right? So you cannot do that when you watch YouTube sessions, which you can, right? So that's why feel free to ask questions. You can write to the chat box or you can unmute yourself and ask questions. So please do not hesitate because this is really important that you ask questions. And there's no silly questions. We are all here to learn. So please do not hesitate. I am open to any kind of questions. All right. So if everything is okay, I would like to share my screen at start. So I hope you see my screen. Could one
yes, it's
okay. All right, great, thank you. So today we are going to talk about homology first, because we have to understand what homology is. So it would be great if we can make it interactive. So if there is any answer regarding homology, I would like to hear that. So first question is, what is homology? Does any of you have any idea about, or have you heard of it? You can write to the chat box too. Have you heard of this term or not? I would like to know. Or you can unmute yourself and speak up. Common ancestor. Yes, exactly, right? So homology means common ancestor. You are totally right. So if two biological units have a common ancestor, they are homologous to each other, right? So this is homology, right? So there are no independent inventions of some biological function or some biological unit, then they are homologous to each other, right? But similarity and homology are often mixed, and they are not necessarily interchangeable terms. So homology and similarity are not same. So homologous units are generally similar, but not all similar units are necessarily homologous. So that's why we have to be careful about that. And now I would like to bring up some at molecular level what homology is, right? So if two or more genes share common ancestor, and if, for example, in this case, this is globin, and all of these genes are basically homologous to each other because they have a common ancestor, right? However, homology term can also be separated into two subterms. What are they? Orthologs and paralogs as well. So we will go into detail at the end of the phylogenetics session, but basically orthology means homology through speciation. Paralogy means orthology through gene duplication, right? So we will go into details later on. But now let's go back to the similarity and homology. So if I ask you this question, so I can ask many questions, but who is the most similar person to this gentleman over there, right? What would you say? So I ask these questions in my lectures too. People tend to answer based on the skin color, right? Or based on the other physical appearances. However, similarity question can also be asked differently. For example, this man and this man seem to be similar to each other based on their skin color. Or let's say this lady and this gentleman, they look similar based on their skin color. However, with respect to gender, for example, two females are more similar to each other. So it really depends on what you ask. So what do you mean by similarity? So similarity doesn't necessarily mean that genetic similarity, right? So it can be anything. It can be from any aspect. So that's why we have to be careful about that similarity issue. So similarity doesn't really ask you the genetic basis. It can ask anything. It can also ask genetic basis, but it's not necessary. So, for example, this can be given. So Sicilians and snakes, they look similar. They both crawl, right? So one may think that, okay, these two things should have some sort of common ancestor, but this feature of crawling, and they are independently evolved. So although they look similar, these two organisms, actually, this crawling feature is not homologous to each other. They are independently evolved. So what we call convergent evolution, basically. So the take-home message here is similarity doesn't necessarily mean homology. So we can give various of examples. We can give dolphins versus sharks, right? Or other examples can be given. So if this is the case, how do we understand homology is the question. And this organismal level can also be seen at the molecular level, right? Two protein structures can be similar, two folds can be similar to each other, and they look exactly the same. However, they are not homologous. How did it happen? And the answer is, again, convergent evolution. So they independently evolve that structure. If you go to molecular systems, you also see that two systems, two repair pathways, for example, because I work in repair, prokaryotic repair and eukaryotic repair systems, they work almost identically. However, if you look at the proteins that are involved in these two pathways, they are independent of each other. So they do not share common origin, but overall system is very, very similar to each other. And it's again convergent evolution. So how do we understand homology then? Whether two entities are homologous to each other or not. So we look at the sequence, right? So we look at the sequence of the genes, because if sequences are similar enough, and if you can align them, and if this alignment is significant, then you have an idea whether this similarity of sequence is due to chance only or not. Right? So that's why we have to apply pairwise sequence comparison. So let's talk about it. So what do we do first of all? So we have two sequences, a pair of sequences. These sequences can be DNA sequences or protein sequences, right? And then we can try many different alignments between these two sequences. Then it means that we need to have a method for scoring these alignments. And then, because we have many alignment possibilities, we decide which alignment is better. How do we decide? We just look at the similarity score, and if the similarity score is maximized at certain alignment, then we decide that this is the alignment, right? So that's why the inputs are two sequences and a method for sequencing one alignment. And then the task is we just basically maximize the score, and output is the overall alignment. And why do we do alignment? Because first, we would like to infer homology, whether two entities, two genes, two proteins that derive from common ancestor or not. All right. So we say that, okay, if we align them and if the significance is there, then we say that, okay, these two entities are homologous. And most of the time, we can infer structure and function through pairwise sequence alignment. Because in the experimental labs, it is not possible to study the entire protein universe, right? So, for example, human protein X can be studied in the lab, but horse protein X, which is homologous to human protein X, may not be characterized in the lab. And it's never going to be, because it's almost impossible to characterize all proteins and enzymes or receptors in the lab. So that's why, so what we do, computationally, we infer homology, and we at least have an idea regarding the function, because we studied human protein X in the lab. We haven't studied horse protein X, but because they are homologous, and if the degree of homology is high, then you say that, okay, probably this horse protein has the same function as human protein. So that's why it also gives us regarding, gives us information regarding the function and structure of the unstudied proteins. So as I said before, homologous sequences can be divided into two groups. So we say that ortholog sequences are homologs basically, but they are derived from speciation, and paralog sequences that are derived from gene duplication events. We will go into detail regarding them, and they are important. So there are some technical issues in sequence alignment. So the sequences that we are comparing can have different lengths. Or another issue is maybe only some portion of these two proteins align with each other, but the rest is not homologous. Maybe there is only one region that are homologous, and it happens. So especially if you just align proteins, and you will see that some domains are common in some protein sequences, and the rest of the protein has nothing to do with each other, right? So we need to allow partial matches because there are some mutations. And we also know that some amino acids are more likely to substitute each other. So that's why partial match is important. And there are various of insertions and deletions that we have to take into account. So there are several sequence variations. Let's go into detail about them. So some of them are substitutions, some of them are insertions, like here. So this is substitution C to G. Now, if you want to align these two sequences, you have to infer that C and G had a common ancestor, right? So that's why if you can infer that, normally C and G may not be aligned if they were alone, but by just looking at their context, their neighbors, you can say that, okay, this G and C probably had a common ancestor, right? So also insertions. So this is an insertion, for example, AC, then these four letters are inserted here. So that's why insertion is also a problem in sequence alignment, as well as deletion. So some part of this sequence might be deleted. So how do we take these events into account? So for substitutions, we have to allow some mismatches. First, this is important. And second, for insertions and deletions, if one sequence has an insertion, for example, then how do we represent it in the sequence alignment? We basically use gaps. So this CGGA subword has no corresponding homolog in the other sequence, let's say. If this is the case, then what we do is we just insert gaps in the other sequence, right? So because there is no corresponding homology. So that's why these issues are important to take into account in sequence alignment. So how does it work? Yeah, I mean, why do we have insertions and deletions in proteins, right? So protein has a sort of fold, it has a structure, and any kind of sequence insertion or deletion might prevent proper functioning of the protein, because we know that proteins have 3D structure, and if you just go into detail, it has 2D structure, which is basically beta sheets and alpha helices. But why do we have insertions and deletions? It is most likely, so when you see insertions and deletions, they are in the loop structures, and which are not necessarily sort of very important in protein function. So that's why they are not that significant. So always there are exceptions. So these are the regions where we see most of the insertions and deletions. Okay, so this is basically an example alignment. This is not pairwise alignment, multiple sequence alignment, but what I would like to show you is the gaps here. So you have to introduce gaps because there's an insertion here, obvious insertion. And for example, there is deletion here, right? So, and this is also obvious deletion. So this is one thing that I would like to show. And another issue that I would like to highlight is the conservation levels. So if you just look at the multiple sequence alignment, you will see that some regions are, some amino acids are 100% conserved across different globin proteins, and some amino acids are not that conserved. So that's why we can also infer from alignment what is the most important, or what are the important amino acids in the protein function, right? So because this conservation doesn't mean that there were no mutations. Actually, there were mutations in that spot. However, those genes and proteins are not selected because they, those changes did bring some disadvantageous situations. So they reduce the fitness of these protein, okay? So that organism. So that's why they are not selected. So today, what we see as conserved is going to be functionally important just because of that concept, that evolutionary perspective that we have. So there are three key questions here. So first, what do we want to align? Second, how do we score an alignment? And third, how do we find the best alignment? Okay, so I would like to give you some examples regarding to that. It may be sort of a little bit detailed, but I think it's important to understand the essence of this alignment strategy. So there are two main types of alignment. One is called global alignment. The other one is called local alignment. So what are the differences? So in global alignment, you just try to align the entire length of two sequences, okay? And this is sort of has a hypothesis that the entire sequence is homologous to the other one. So this is some sort of an assumption that you have if you force global alignment. On the other hand, local alignment doesn't necessarily have that assumption. So you just look at these two sequences and try to find the best subsequence match. And from local alignment, you can also go to the global alignment as well. This is another story. And semi-global alignment can be the third option. It is, again, find best match for the entire length, but not necessarily entire length. So you just have some sort of a compromise at the ends of the sequences. So you don't really penalize gaps on the ends of the alignment. So this is called semi-global alignment, but most of the time it's important to understand the difference between global alignment versus local alignment. So it is just an example of a very, very short two sequences and how various pairwise sequence comparisons that you can make, right? So let's say that we have two words, E and V, V, I, S, okay? We would like to align it first. So how many possible alignments that we can have? So here are the examples. We can have no gap. We can align E to V, L to I, V to S. Or you would like to align E and I for some reason, and then you have to introduce gap here and gap there. Or you would like to align V and V together, then it means that you have to introduce gaps over there. So on and so forth. So even with these only three letter words, we have many possible alignments, right? So what do we do with these alignments? So first, we have to score it, right? We have to score this alignment. What alignment or out of these possible alignments, which one is the best one? So that's why we have to find a way to score them, right? So there are two things that we have to consider. One is gap penalty function, because you have to give some penalty scores to gaps, because if you don't, then there will be all gaps. So it will be three words and three words there, three letters, and each letter will correspond to a gap. So this is not alignment, right? You just place them consecutively to sequences. So that's why we have to have a penalty function for gaps. And second thing that you need is a substitution matrix. So what does it mean? So it means that what is the likelihood of aligning E and S versus E and I versus E and V, right? Or V versus V. So you have to have a substitution matrix to be able to tell the likelihood of this pairwise sequence alignment. So it means that we need to have two important functions or two important elements in scoring the alignment. So let's talk about gap penalty function. So there are several scenarios, right? So one of them is maybe you can assign a single constant penalty, right? So G is constant, and then you just give the same penalty score. Okay, so this is one way. The other way is maybe the penalty score should be correlated with the length, right? So this is called linear gap penalty function. So you have your penalty score times K, and K is going to be the length of the penalty. So let's consider this. Now we would like to score this alignment. How do you do that? First, you just get from the substitution matrix, what is the score of aligning V and A? And here, this is the score. A and I, this is the score. HQVL. Then, this is linear function used here. 3 times G. And G is penalty score for single position. And this is 3 times G. Now you have substitution between D and G. Now 2 times G, and so on and so forth. So at the end of the day, we can have a score, right? It's easy. But there are more possibilities to score or penalize the penalties. So what are they? So this is called affine gap penalty function. So what it says is, so once you open a penalty, once you open a gap, you shouldn't really penalize much based on the length. So there should be some penalty for that. However, opening a gap alone is important, and it is more important than extending the gap. So that's why what it does is, so it gives a constant A for opening a gap, and then the rest, it reduces the weight of the length of the gap by assigning sort of a lower penalty score here. Okay, and finally, convex gap penalty function. So it is similar to that. What is the difference is this portion. Now it is not linear. I will show you an example. And finally, we have a profile-based gap penalty function. We'll talk about profiles, and it is a very, very important concept, and we'll cover that later on. So at the end of the day, this is how it looks like, right? So constant gap is the green one. So whatever the gap length is, so you always give the same score. So, or you can say that, okay, this is linear, this has to be linear. Or you can say affine. So if you just look at this, it doesn't start from 0, it starts from 2. It means that it just gives an opening penalty function. Then the rest is linear, okay? And convex is sort of different than linear as well. So most of the time, affine gap penalty function is the best practice. So it is mostly used across algorithms. And how do you find the best alignment? This is a major question. So if you would like to calculate all possible alignments, first we have to ask how many possible alignments that we can. If two sequences have length of n, so how many possible alignments that we might have? It is this value, okay? And if you have two sequences with 100 as length, so how many possible alignments that we can have is 10 to the power 77. This is a huge number, right? So there is no way to calculate all possible scores of these alignments. So that's why now we have a problem. How do we do that? How do we get the most likely alignment between across these possible alignments, right? So this is the question. Then dynamic programming comes in. So we will not really get into detail as much, but basically dynamic programming takes the advantage of solutions for the subparts of the problem. What does it mean? So you just calculate some instances and then you get the most likely sort of path and you just build upon that, basically. Rather than searching the entire universe, which is impossible, you just get a path by considering the most likely scenarios and then you have a route there. We'll see an example, but this strategy first used in Needleman-Wunch alignment, which is the sequence alignment, pairwise sequence alignment. So let's give the example of this. So let's say that we would like to consider the last step of these two alignments. So how do you align this? Whether C and C is going to be aligned, C and gap, or gap and C is going to be aligned. So what you do is basically you consider the previous step, which is the most likely, right? So then after you consider the most likely, the best alignment for the previous step, then you build on top of it, and then you go from there. So this is a sort of a nice tool that we can use. So we have a matrix here. So we have AGC here, AAAC here. So what we would like to do is we would like to align them, right? So we first create a matrix here, and then we'll score. This is going to be the score of the best alignment of AAA versus A to G. So how do we do that? We basically select the maximum of these three values. So what are they? So if you just consider I and J as the positions, so I is the position in the first sequence, J is the position in the second sequence. So what you do here is, in the previous step, you basically have the alignment score of F, I minus I, J minus I. This is the alignment score of the previous sort of step. And then the substitution, from the substitution matrix, you have a score of aligning X and Y. So Xi and Yj, basically. So X is one sequence, Y is the other sequence, I and J are the positions. Or what you do is you basically have a score of insertion. So in this case, you have the substitution or alignment score of a function of I minus 1 versus J plus the gap penalty score. And here the vice versa. So the gap is introduced in the other sequence, I versus J minus Y plus the gap penalty score. So after you have all the scores, what you do is you would like to get the maximum of them, and then you just select the maximum scenario, and at Ij is going to be the maximum of these three values. And this is one way to specify the dynamic programming. Okay, so let's get an example. Again, maybe we don't have time to work on it. Normally, it would be a nice activity to do that, but I would like to give the basics of it. So how do you do that? First, we initialize the matrix, and we initialize the first row and column of the matrix, right? So how do you do that? We will basically introduce the gap penalties. We'll come to that. So just like this. So AGC and AAAC. So this is 0, okay? Then if you come to here, it means that you introduced a gap here in this sequence. So this is aligned to a gap. This is what it means. So this means that this cell means that this A is aligned with A, okay? So if this is the case, we can easily initialize the first row and first column, which is basically going to be gap, now 2 gaps and 3 gaps. And same thing here, gap, 2 gap, 3 gap, and 4 gaps, basically, right? So after you initialize them, you have to have some sort of a score, basically aligning the match or mismatch. So let's get that example. So in this case, the substitution matrix is given as if there is a match, you just insert +1. If there's mismatch, then the score is -1. And if there's a gap, the score is -2. Now we can fill in the blanks. Okay, so now instead of G, we will write 0, -2, -4, -6. And then for each cell, we will consider the maximum of these 3 scenarios. So basically, this is how it's going to be. Again, I'm not showing in detail, but what we do here is basically we take the maximum of whether the gap or match or this gap is going to provide the maximum score and choose what is going on here, okay? So basically, let me give you one example. So this is -2, right? And this is a match here, A and A. Remember what we have. Match is +1. So -1 + 1 is going to be -1. So it's going to be -1 is one option. So here, -2, and this is a match, +1, it's going to be -1 coming from there. And here, this is 0, and this is a match, AA +1. Therefore, we are just comparing +1 versus -1 versus -1, which is the maximum. +1 is the maximum, then we just place +1, okay? This is the logic, and you just screen the entire matrix through that. And after you do that, what you do is basically to find the best alignment, because you will remember where you come from. Okay, you come from 0 to 1. And then you will know that you come from this cell to that cell. And then you will say that, okay, I chose the maximum value and I came from this cell to that cell and this cell to this cell. So at the end of the day, what you have is a root here, which is represented in green arrows. So what does it mean? It means that, okay, this C and this C is aligned, just like here. And then if you come here, there is a sort of a gap, okay? It means that this A is aligned with nothing. So then it means that there's a gap here, A versus gap. And then you have G and A, which is aligned. And then you have A and A, which is also aligned, okay? So this is one of the optimal alignments that we can derive from basic Needleman-Wunch algorithm. So do we have any questions so far? Let's see. I guess not. I hope it's clear. Okay. So I would like to cover local alignment too before the break, I guess. So this was the global alignment so far, okay? Now we have to talk about the local alignment. And again, we can apply a very similar strategy. And how do we do that? So the aim here is to find some sort of a subunit of a protein that is aligned with the other one. So why it is necessary? You know, protein domains, basically, or DNA motifs, they are not really conserved throughout the protein, right? So they are only parts of the protein that are conserved. And that may be sufficient for protein function or for DNA function. Maybe it's a transcription factor binding site and they are homologous to each other and you would like to identify that homology, right? So that's why local alignment is super, super useful because if you don't know what to look for, if you are just looking for detecting homology event, then local alignment is very useful. And it is very, very sensitive for highly diverged sequences. So that's why rather than global alignment, local alignment is widely used. Now the algorithm is similar to Needleman-Wunch and Needleman-Wunch. Now we have Smith-Waterman algorithm for local alignment. Now instead of getting the maximum value here, this case will have 0, okay? So because you are not interested in aligning the entire global, and globally aligning the entire length of the sequence. So that's why now instead of having 3 options, now we have the 4th option, which is 0. And there's also one more difference. And we will initialize the first row and first column with zeros, okay? Then we'll trace it back. So I will give you an example. So this is a different example. We would like to get a sort of a local alignment here. Okay, how do you do that? So let's get, and again, the +1 for the match, -1 for the mismatch, and gap is 2, -2. So in this case, you initialize zeros, okay? And then you'll say that, okay, A and T is mismatch, right? So this is going to be -1 from this cell, -1 from this cell, -1 from this cell. But you get the maximum of these -1s and 0. So in this case, it is going to be 0, right? So that's why this is how you generate it. And now finally you have a match here. You get the maximum of these values, which is going to be 1. And this is going to be, again, 2, because the maximum is going to be provided from this cell. 1 + 1 is going to be 2. And this is again a match. 2 + 1 is going to be 3. And finally, there is some sort of a gap here. So what is the local alignment? Basically, it is A aligning with A, the second A is aligning with A, and the third position G is aligning with G. So the local alignment is going to be AAG. So if you just look at these TTs, they are not shown in the local alignment because we are not interested in it. And the same thing is true for this A as well. We are not interested in aligning this A because this is called local alignment, okay? So this is a nice example of why we need local alignment. So if you have 2 sequences here, if you force them to be globally aligned, so this is what you get, okay? So some sort of an alignment, and this is a nucleotide gene sequence alignment, let's say, okay? So there are some sort of partial matches, okay? And this is, okay, I mean, it's not a big deal to get the global alignment because there are only 4 letters. You will get some sort of an alignment, right? As long as they are not hugely different from each other. But if you just apply local alignment, there is a perfect match here in this position. And this is just perfect, right? There is no any mismatch. So which one would you trust? This global alignment or local alignment? Which one would give you the real homology alignment? Actually, it's going to be the local one, right? So that's why, especially for DNA sequences, local alignments are very useful. It is also useful for protein alignments, but because the lack of overall variety or variance in letter number, I would say, the number of letters is only 4 in gene sequences, then local alignments work just fine rather than global alignments. So this is not saying that global alignments are useless. It is useful, they are useful, but for detecting homology, we have to use local alignment. However, if we are sure about the entire length homology between 2 genes, then feel free to apply global alignment. So it doesn't hurt. But this is a nice and sort of, I think, important example of showing the difference between global and local alignment. Okay, so one thing that I would like to highlight is, so far we said that, okay, substitution score is if there's a match, it is 1. If there's a mismatch, it is -1. But is it really so, right? So can we have better substitution scorings between the two sequences or between amino acids or nucleotides? We'll talk about them, but let's give a break. And so let's give 15-minute break and come back at 9 o'clock, okay?